Please confirm that you can see the presentation.
Yes, sir.
Thank you. Okay, so in the last class, we began the discussion on dielectric materials. This followed our previous discussion on dipoles. So, and in relation to that, we touched upon the idea of polarization. So I'll just briefly recall the salient points of what we talked about, what we discussed in the last class regarding polarization, of course, that polarization is a phenomenon that is typically, but not exclusively, associated with dielectric materials. What are dielectric materials? They are insulators. And what is the most important property of an insulator? That they do not have free electrons or free charges, as metals do. And so, in an insulating material, the atoms also keep the electrons to themselves, even in their bound state. And as such, there being no free charges, there's no free passage of currents, a current. Nevertheless, under the effect of an external electric field, the overall charge neutral atom can still be polarized. So we discussed this phenomenon with respect to atoms, in which we have, by the application of the external electric field, we have a polarization by distortion. This kind of a feature will be absent when there will be no external field. And what is this polarization by distortion due to? That whenever you have an electric field, it tends to sweep positive charges forward in the direction of the electric field and drag negative charges backward in the opposite direction. So that is what you have. Whereas there could be other systems where there could be permanent dipoles, such as in molecules, water molecule, for example. They already have a dipole-like structure, and when you apply an external electric field, the effect of the external field will be to just rotate the molecules such that the positive charges are aligned in the direction, are pushed or rotated in the direction of the electric field, and the negative charges are rotated to a position opposed to it. So that way the molecule will be aligned along the direction of the external field, such that the positive charge will be towards one end and the negative charge will be to the other end. The positive charge will be towards the forward end of the electric field. So this will be polarization or rotation by alignment. Okay, so this happens in the case of systems where the dipole structure is already present. Usually such a thing happens in the case of molecules. What is, therefore, so now we shall have to quantify our discussion. So all of these things are to be qualitatively understood so far what we have talked about, but now we have to bring in some quantitative ideas. And what are the quantitative ideas? The quantitative ideas are the idea of, first, the idea of a dipole moment. What is a dipole moment? Small p, vector p, is defined as the charge. So whenever you're talking about a dipole, there are two charges, a positive charge and a negative charge. And so the dipole moment is defined as the product of the positive charge times the displacement between the two charges. And since the displacement is a vector quantity, displacement is a vector quantity, what is the direction? So it's very natural to ask, what is the direction of the displacement? The direction is from the negative end to the positive end. This negative end is the initial point and the positive end is the destination point. So from the minus sign to the plus sign, you draw the shortest path, and the direction from the minus to the plus end is the direction of the displacement. So that into the positive charge is defined as the dipole moment. Okay, so in the case of atoms, this point I'm stressing once again. In the last class, I caused some confusion about this thing. In the case of atoms, you can immediately see that if the electric field is withdrawn, the dipole structure will be lost. So in the case of atoms, stronger the external electric field, stronger will be this distortion, this stretching, and greater will be the dipole moment. Therefore, there's a proportional behavior between the applied external electric field and the dipole moment, and the proportional factor is known as polarizability, or more specifically, atomic polarizability. And of course, there's also the potential energy. You can immediately see the potential energy will be minimum in the case of rotational alignment of a permanent dipole in the direction of the electric field. The potential energy will be minimum when there is a zero angle between the two vectors, the dipole vector and the external electric field vector, in which case this potential energy will have the lowest value. Why so? Because the minus sign makes it have the lowest value. The highest value will happen when you have 180 degrees. In that case, it will be cos 180 degrees. First, minus magnitude of the dipole moment into the magnitude of the electric field into cosine of 180 degrees, and cosine 180 degrees will be -1. So -1 into minus will be plus. So that will be the maximum energy. So usually the alignment is happening because there's a tendency of this sort of a system to minimize the energy. Okay, and then I have stressed upon these points that atoms do not have a permanent dipole moment, but molecules do. So former kind of systems are non-polar substances, material, and the latter are polar material. Water is, of course, a famous example. It's a very standard example of a polar solvent. Okay, now this was the point where we ended. Let us bring in the idea of polarization. What is polarization? I mean, polarization vector, that is. Polarization. Suppose, let us just refer to polar molecules which already have a dipole structure. So initially, in the absence of an electric field, these polar molecules will all be randomly oriented, and all the dipole moments will also have random directions, and therefore the sum of these little dipole vectors, net sum, will be nearly zero. Okay, but when you apply an external electric field, there will be a tendency towards alignment, and so the alignment will cause all these little dipole vectors to reinforce one another's effect, and as such, you'll have a large sum. So polarization is defined as the sum of all the total, sum of the dipole moments, the total dipole moments, sum of all the individual dipole moments divided by the volume of the system. So if you have a glass full of water, and so the sum of all the water dipoles divided by the volume of the water in the glass will give you the total polarization vector. So dipole moment, total dipole moment per unit volume. So these are the ideas we shall now carry forward in what we are about to begin discussing. First, we shall talk about the idea of bound charges. Let us see. Remember, free charges carry a current, and free charges are associated with conductors. Whereas insulators, of course, they are made up of charged material. Everything, conductors or insulators, are made up of charged materials. If something is made of an atom, it has to be made up of charged material, and positively charged nucleus and a negatively charged electron, all these things. However, what distinguishes a conductor from an insulator is not the presence or the absence of charges, but the presence or the absence of free charges. If you have free charges that are free to move around within the body of the conducting material, then you have a conductor. Whereas if the charges are bound to, all the electrons, let us say, are bound to their parent atoms, then you have bound charges, and such a material will be an insulating material. So we look at one such thing. There's a schematic diagram. So here's a rod of an insulating material, let us say, the sort of thing that you would put between two capacitor plates. I hope you are able to recall that between two capacitor plates, you can put what is known as a dielectric material. So A dielectric material is an insulating material. Okay, let us now see. So here's the diagram. Let us try to follow the diagram here. Here's a rod. For simplicity, I've drawn it like a cylinder, and it is full of bound charges. There are no free charges in this rod. And there's an external electric field E here. There's an external electric field that is coming from the left going to the right. As I mentioned to you earlier also, the external electric field will, the effect of any electric field is to push positive charges forward and draw negative charges backward. So these charges, of course, are bound. Nevertheless, they will undergo a little polarization. That is to say, under the effect of, just like here in this atomic figure, overall this object is charge neutral and the electron will be bound to the atom. You can't separate them. But the effect of the electric field is to just cause a little bit of disturbance and a little upheaval, so by distortion. So the positive charges will be pushed forward and the negative charges will be dragged backwards. And so here you have something similar. So you have positive charges pushed forward and negative charges drawn backward. Okay, now let us see what happens over here. So at the end of this material, there will be a bit of a pileup of positive charges at this end of the rod, and at this end, the left end of the rod, there will be a small pileup of negative charges. In the bulk of the rod, try and follow carefully, although this diagram is oversimplistic, but it still conveys the idea, I hope. In the bulk of the material, all the pluses and the minuses, this plus and this minus, this plus and this minus, this column of 3 pluses and this column of 3 minuses, and likewise this and this, they will they are in the neighborhood of one another and they'll cancel out the effect. So as if suddenly this rod has got overall charge neutrality in the middle region, but at the end there is an uncancelled collection of positive charges, and at this end there's an uncancelled collection of negative charges. So this whole thing has suddenly become like a giant dipole, a plus end at one side and a minus end at the other. Okay, let us now try to look at it in greater detail. So if the total amount of charge gathered at this end is plus Q, and then you say that the total amount of charge gathered at this end is Q prime. Okay, but then the plus here will be equal to the minus here in number. So Q prime, the number of negative charges, will be equal to minus Q here. This is the positive end. Q amount of charges has gathered over here, and minus Q has gathered here. So Q prime is equal to minus Q. Okay. The length of this rod is D. And the area of cross-section of this rod is A. So first, there are two ways of looking at the total dipole moment of this system. What are the two ways? First is charge, positive charge Q times the displacement D, Q into D. That is the dipole moment. I'm just referring to the magnitude for the time being. So just the magnitude of it that you have, Q into D. Okay. There's also another way of looking at it. Just a while ago, I said that the total dipole moment, or the polarization vector, is equal to the total dipole moment divided by the volume. Therefore, the total dipole moment is the polarization vector into the volume. So you can look at it like that also. Total dipole moment, Q into D, is also equal to polarization into the volume. And what is the volume? Area of cross-section, capital A, multiplied by D. So A into D is the volume, P is the polarization. So that is one way of looking at the dipole moment, P into A into D. And the other way is Q into D. Okay, so if this is equal to this, then the two D's will cancel and Q will be equal to P into A. Okay, so there is something to look at in this particular formula. Q is equal to P into A, and a few points also. First, there is a statement. You have a uniform polarization, that all the charges are smoothly cancelling, the positive and the negative charges are smoothly cancelling one another out within the bulk of the material. But at the end of the material, on the open exposed surfaces, the disk faces, this here and this here, the right disk and the left disk, at the end of the material, the bound charges have piled up at the end. So it's a surface effect. So charges have piled up on the surface of this polarizing material. This is a surface effect. And what is the bound surface charge density? Why? It is going to be charge divided by the area, Q by A. Q by A is also equal to the polarization, but then that is also equal to sigma, sigma as in surface charge density, subscript B as in bound, B bound, sigma surface charge density. So bound surface charge density is magnitude-wise equal to the polarization, magnitude of the polarization vector, Q by A, Q divided by, so total amount of charge gathered at this end divided by the total area will be Q by A, and that is the bound surface charge density, and that is equal to P. Okay, so that's the bound surface charge density. Now we extend this idea, generalize this discussion to the case of non-uniform polarization. What do I mean by that? Here we have talked about a very nice, neatly aligned figure. You have a well-ordered atomic or molecular structure within this thing. So there we have this thing will be the electric field that is passing through this thing uniformly polarizes this material. This external electric field in this nice, neatly aligned structure, the external electric field uniformly polarizes this material. Okay, so far so good. You just excuse me for a minute, please. Yeah, sorry, thank you. But then there could be other ways of polarizing a material. Non-uniform polarization is one such effect. Suppose for some reason there is due to something, a local electric field has caused a polarization. This is not a local electric field, it is coming from outside, and globally, all throughout this material, it has caused the polarization. But here, a small local electric field due to something, we don't know what, but due to something, a small local electric field has caused a polarization. So what is the feature of this electric field? These arrows, let's say it's some burst of an electric field, whatever has caused that thing, has happened. So the electric field lines are going out in the direction of these arrows. Once again, it's an overly simplistic diagram, but let me stick to this diagram for the sake of conceptual clarity. You see that this electric field is non-uniform. What do I mean by non-uniform? If you look at this diagram, anywhere in this rod, the external electric field will have the same value, right? But here, the electric field will have a stronger value inside, and as you are going out, the field lines are getting more and more spaced away from one another, and therefore the electric field lines are getting more, the electric field strength is getting more diluted as you're going outwards. So this is a situation whereby you have a non-uniform electric field, and a non-uniform electric field will cause a non-uniform polarization. How so? Let us now try to see. The electric field lines will push positive charges outwards. So these pluses are being pushed outwards from this region. So this region, before these arrows came to be, this region had a homogeneous mixture of positive and negative charges before these arrows was set up. But now these arrows have separated the positive and negative charges, and the electric field lines are pushing the positive charges outwards and gathering the negative charges inwards. You can immediately see why I'm calling this non-uniform polarization. First, let us count the charges. 1, 2, 3, 4, 5, 6, 7, 8, 9 plus charges. And likewise, there will be 9 minus charges. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 minus charges and 9 plus charges. However, now you note one thing. Here, 4 plus charges and 4 minus charges were packed in the same area. I hope you are able to understand that thing. Plus charges and minus charges were packed in the same area. Therefore, the polarization could be termed as uniform. But here, the positive charges are spread out over a larger area, and the negative charges are gathered in over a smaller region of space. So you can immediately see that this is a situation whereby you will have a non-uniform polarization. It's a local effect. And as I've said, written over here, creates bound charges within the volume. So within the volume, here, the bound charges were on the surface of the material at the plus end and the minus end, but on the two exposed surface. But here, these bound charges, these negative charges are now within the bulk of the material. There is no exposed surface, so to speak. This is just a hypothetical circle I've drawn. It is just that the positive charges have been pushed out and the negative charges have been gathered in. It's somewhere in the depth of the material, not on the surface. So this is a bulk effect, non-uniform polarization that you have had. Okay. Now we will upgrade this discussion a little. Let us see. Rho B is the charge density, as you've had in the formula. Divergence of E is equal to rho by epsilon naught. So rho is the charge density. And here we are not talking about any kind of charge, but a particular kind of charge which are bound, meaning that they'll be shifted a little, but not travel far. It's just like these charges are put on chain, like let's say a dog, a pet or something. You put the animal on chain, so it will just be able to move around a little and go only as far as the length of the chain would allow it to, and no more. Whereas free charges don't have anything to chain them to anything else, and so free charges can move as far as possible within, of course, the bulk of the material. So here, rho subscript B, B as in bound, you have bound charge density. So what is the total amount of charge contained in this part, in this region? Rho B into d tau with a volume integral. Charge density, volume bound, volume charge density, rho B into d tau, which is d tau is the volume element, and take a volume integral. What I'm writing here is actually this formula. Q prime is equal to minus Q. This formula only, but Q prime, the negative end, this part is written as rho B d tau, volume integral. And the right-hand side will be minus Q. So minus here. So you have minus here. And then what about the positive charges? The positive charges have all floated to the surface, this imaginary hypothetical surface. So what is the total amount of positive charge on this spherical surface? Surface charge density multiplied by the area and integrating all throughout. And what is surface charge density? Surface charge density is magnitude-wise, it's equal to the polarization vector. We have just discussed that P is equal to Q by A, and that's also the surface charge density. Charge per unit area, Q by A. So the right-hand side will be P dot dA. It's going to be a scalar, of course, but area is a vector quantity, and so is polarization. Take the dot product of the two things to get scalar. Outcome will always be a charge. I've written something over here. Why the negative sign? Well, this is the answer. Q prime is equal to minus Q. This is just this simple formula written in slightly complicated form in accordance with the generality of the problem that we are looking at now, the physical problem that we are looking at now. And also I've written something here, polarization flux. What is polarization flux? Any vector dot d area, any vector dot with an area element integrated over the full surface will give you the flux of that vector. E dot dA or B dot dA integrated over some surface area. So closed surface integral. So minus P dot dA. So I hope you have understood this particular point. This equation that we have over here is simply a generalization of this equation. Q prime is equal to minus Q. Okay, with that, now we will, so the physics part has come to an end. Now we'll just apply some mathematics. The Gauss divergence theorem, with which you are quite familiar by now. The Gauss divergence theorem will say that the divergence P d tau volume integral will be equal to closed surface integral of closed surface flux of P dot dA. So that's the Gauss divergence theorem. So you look at this formula, P dot dA closed surface integral. So that we will substitute by this thing. So you will have rho b d tau from this formula V, and this P dot dA closed surface flux will be replaced by a volume integral of the divergence of P d tau. So there's a volume over here. So there should be a subscript V here as well. So that point I'll add. Okay. Right. So all you have to do now is to notice the equivalence between the two. Here you have rho b d tau, volume integral is, so volume integral and volume integral d tau and d tau. So all you just have to do is to the right, divergence of P is equal to minus rho b, bound volume charge density. That is the point. Okay. So with that thing, we can now further extend our argument. See, no material is a perfect conductor and no material is a perfect insulator. A perfect conductor also has a bit of resistance. The charges tend to be sluggish, not move as freely as we would want to. If they had moved completely freely, then you would not have to keep a potential difference all the time to make the charges move around. Incidentally, charges do move without the application of a potential difference. I mean, can move in a resistance-free manner, but those are special cases, as in the case of superconductivity. But I'm not getting into that discussion now. So charges can't, even in the best of conductors, let us say copper or silver. Copper is a more ready example because silver is much more expensive than copper. So even in the best of materials, conducting materials, there is a little bit of resistance. And in an insulator, there's an extremely high resistance. Charges tend to move not at all. Okay. Nevertheless, a little bit of trickling movement should be there. So in general, no material is 100% a conductor, and likewise, no material is 100% an insulator. So in the case of an insulator, the current will be so weak that you will tend not to feel anything at all, whatever. So in general, a material will have a combination of both free charges as well as bound charges. An overwhelming domination of free charges will make the material a conductor. An overwhelming domination of bound charges will make the material an insulator. But in reality, both kinds of charges will exist. So the total number of charges will be the simple sum of the free charges and the bound charges. And accordingly, the charge density will also be the sum of the bound charge density and free charge density, free charges as you have. You'll say, where are these free charges coming from? Well, they could be injected extraneously because, of course, after all, the system left to itself can only supply electrons or anything from its own atoms. But in an insulator, the atoms are bound really as a general rule. So maybe you can inject some extra charges from the outside to give it some sort of conducting property. So whatever it is, so the total charge density is the sum of the bound charge density and the free charge density. Bound charge density as given by this formula. Okay, now let us go to Gauss's law of electrostatics in the differential form, with which you are familiar by now. Divergence of E is equal to rho by epsilon naught. This is one of the Maxwell equations. Divergence of E is equal to rho by epsilon naught, and then this rho I'm decomposing into two quantities, rho free, density of the free charges, and rho B, density of the bound charges. Okay, and so divergence of E is equal to rho free plus rho B, epsilon naught into, epsilon naught is a constant, universal constant, so I can take it to the left-hand side. Divergence of epsilon naught into E. It's a constant quantity, so divergence is a differential operator, so constant quantities can go inside and out of an operator most freely, no problem at all. So I put it inside. Okay, then I'm writing divergence of epsilon naught into E is equal to free charge density, and then rho B I'm substituting with this minus divergence of, sorry, yes, minus divergence of P. Okay, next I'm taking this divergence operator from the right to the left hand side, gather all the divergences on one side. Divergence of epsilon naught into E plus P is equal to rho free charge. Okay, here's something very important. I define a new vector known as the electric displacement vector, capital D. Capital D is equal to epsilon naught into E plus P. Okay, and then this I'm putting here, epsilon naught into E plus P, I'm writing as D. Divergence of capital D, the electric displacement vector, is equal to the free charge density. So this is basically Maxwell's equation in a dielectric material. Well, this is a general form of Maxwell's equation. Divergence of E is equal to rho by epsilon naught. You don't really prescribe anything about rho when you write this thing, but then let's say that you are in a dielectric material where then you have to worry about the nature of the charges you are working with, free charges and bound charges. So with that, it's just a little trick. But I mean, whenever we talk about Maxwell's equation, be it understood that I shall be referring to this thing. Divergence of E is equal to rho by epsilon naught. I mean, this D we will have to put up with at times. Okay, so it's the electric displacement vector, and P is the effect of polarization in a dielectric material, in a dielectric medium. See, if you are not working with a dielectric medium, then there is no issue about bound charges. And in which case, there's no issue again about polarization. The charges are not going to gather on surfaces or anything, or wherever here, or bunch up here or there. They'll just keep moving freely. And so there will be no polarization. Polarization is what? Separation. Positive and negative charges. You separate, right? So, or let's say, I mean, in general, whenever you say polarization, you are saying that things are separated into two opposite types. Like you say in common conversation, you say politicians are polarizing society, right, for their votes. So like that kind of a thing. So here, the electric field is polarizing this material into positive and negative ends. So they're like that. But if there is no boundness of the charges, there will be no polarization. So everything is moving freely. So then P will be equal to 0 in a non-dielectric material. In a dielectric medium, P will be non-zero. But if you are not talking about a dielectric material, medium, then P will be equal to 0. Then you just have the divergence of epsilon naught E is equal to free charge density, and the free charge density is just equal to rho. There will be no bound charge. Bound charge density will also be equal to 0. Okay, so there is something to be stressed upon over here. What is the nature of E in this whole business? See, when you are writing this external electric field E here, sorry, this electric field E, now be it understood in a very general sense. As soon as you separate charges in a dielectric material, the separation itself will give rise to an electric field. Charges are separated. It's just like, you know, without any polarization, the charges will be uniformly mixed up. But when you create a polarization, the charges will be separated. So immediately from the positive end to the negative end, electric field lines will start going. So the polarization process itself will give rise to an electric field within the system. In addition, the polarization was in the first place created by the external field. So let me just go back to the diagram and try to explain this thing a little. There is an external electric field, not E, for the time being. There's an external electric field that has given rise to the polarization. The polarization process itself will give rise to another electric field. So now you are looking at two electric fields. One is the external electric field, which caused the polarization in the first place. And then the polarization itself has created its own internal electric field. So this E that we are talking about, this E that we are talking about in this thing, is the total field in the medium, both due to the effect of the external field as well as the field that has been created following the polarization within the medium. That is what you have. Anyway, so we are now entering the last topic of electrostatics. It is linear dielectrics and susceptibility. Let us see what we have got over here. Here is this formula, right? If you look at this formula, epsilon naught into vector E is added to vector P. Now you can only add two things if they are dimensionally the same. By dimension, I mean the physical dimension. I'm not referring to the spatial dimensions of X, Y, and Z. Physical dimensions as in mass, length, time, the dimension of mechanics. Then when you bring in electricity, magnetism, you have current. Current, incidentally, is considered, when you bring in electricity, magnetism is considered a mechanical dimension. But there is also the older school of thought that instead of current, you should think of charge as the more fundamental thing, but it doesn't really matter. You have charge, you divide charge by length, you get current. Or you have current, you multiply current by length, you'll get charge. Current is charge per, I'm sorry, divide charge per time. Current is charge per time, charge flow per unit time. So you have current. So you multiply that by time and you'll get charge or vice versa, whatever it is. So these are the physical dimensions that we work with. So you can only add two things if they have the same physical dimension. For instance, you can't add length to area because length has got the dimension of, I mean, length, and area has got the dimension of length into length. So it immediately from this formula, you should realize that epsilon naught into E and P have the same physical dimension. So why not then, for the sake of simplicity, write a relationship like this. P is equal to epsilon naught into a dimensionless quantity chi subscript E into the electric field. So you have epsilon naught into electric field because P and epsilon naught into E, the electric field must have the same dimension. So fine. And then to give a separate meaning to P, I capture this separate properties of P in a dimensionless quantity known as electric susceptibility. Therefore, D, the electric displacement vector, is written as epsilon naught into E plus epsilon naught into this dimensionless quantity into E. Okay, these two things must be dimensionally compatible. And so then the next thing that we do is D is equal to epsilon naught into 1 plus chi E into electric field E. And this quantity, epsilon naught into 1 plus chi e, is captured as a total epsilon without the naught. Epsilon is permittivity, and epsilon naught is permittivity of free space with the unit farad per meter. This comes from capacitance. So I hope you are aware of the formula of capacitor. Capacitance. Capacitance C is equal to epsilon naught into, so you have got a capacitor with two plates. The plates have an area A, and the separation distance between the two plates is D. This is a very simple thing. I'm positive that even you all would have studied this thing at school. So the amount of charge that's built up in the capacitor is going to depend on the capacitance of that capacitor, and capacitance is given as epsilon naught into area divided by D. And so capacitance has the formula, has the unit of farad. So farad is equal to epsilon naught into area by length. So epsilon naught will have the unit of farad per meter, farad per length, farad per meter. Now that is what it is. And so epsilon R is known as the relative permittivity. And relative permittivity is also known as the dielectric constant. So epsilon R is equal to epsilon by epsilon naught. That's equal to 1 plus chi e. So, these are some simple formulae. Today we have a tutorial where these ideas will be introduced. So just please make a note of these things. But of course, in the solutions in the tutorial, these will be given to you. But anyway, so that's about the idea of linear dielectrics. Now, but why linear? Let us now go back to the word linear. We are talking about linear dielectrics. What is the property of linear dielectrics? Polarization, you look at this formula. This is a universal constant. So this is like Y is equal to M, epsilon naught into chi E is also a constant, a dimensionless constant. So epsilon, it depends on the property of that material. This is like a straight line passing through the origin. Y is equal to M into X. That's a straight line. So it's a linear relationship. So you're just saying that, I mean, this D is equal to epsilon naught into E plus P. P must be equal to, dimensionally must be equal to this. Otherwise, he could not have written, I mean, this plus sign between the two would not have come about. So you say that there is a linearity relationship between the two, and so this the proportional factor between the two, or the proportional linear proportional constant, is chi e. So this is like y is equal to mx, the dependent variables being e and p. Sorry, the variables being p and e, p, and so this is a fixed parameter between the two. So that's the word linear. And electric susceptibility, just one last point to touch upon, is not as simple a scalar constant as you might think of it to be. Chi e is in general a tensor for anisotropic crystal. Let me just, I mean, I've just written that thing, so that's why I'm just touching on it, on this thing. Is in general a tensor for anisotropic crystals. So what do I mean by anisotropic? First of all, let us try to understand isotropic. Iso means same. So whenever you say something is isotropic, you refer to it having the same property in all directions. Along the x direction, along the y direction, along the z direction, an isotropic material, not anisotropic, but an isotropic material will have the same properties in all the directions. An anisotropic material will have different properties along different directions. First, let me just give you a simple example of mechanical properties. For instance, in your school chemistry, you would have studied about the allotropes of carbon chemistry. Allotropes of carbon. For instance, diamond is an allotrope of carbon. Diamond is just made of carbon. Coal is also carbon. Graphite is also carbon. But these are different allotropes of the same element. Now, if you look at graphite, graphite has got anisotropic mechanical properties. I'm referring to mechanical properties just to give you a simple familiar example. How so? For instance, in your pencil, the lead of your pencil is made of graphite. So whenever you rub graphite on paper, little bits of the carbon material flakes off and it leaves a mark on the paper. So that is your writing. So that is weak mechanical behavior. I hope that you are aware of the way carbon molecules are stacked in graphite. So they form a hexagonal structure, and then planes of these hexagonal hive-like structures are stacked upon one another. So these planes can easily move relative to one another and have sliding motion. But perpendicular to the plane, if you want to hit, then graphite has got strongly resistant mechanical properties. How strong? For instance, you also should know that tennis rackets are made of graphite. So you know very well how powerful tennis players make strong serves, very powerful serves. The ball will travel at great speed. So, and nevertheless, the tennis racket doesn't break under such a great strong impact of such a fast traveling tennis ball. But at the same time, made of graphite, your pencil lead breaks so easily. So easily, in fact, you don't even have to break it. You just scratch a paper with the tip of your pencil, graphite will flake off and leave a mark. So along one direction, so basically when you want to make a tennis racket out of graphite, you just have to ensure that the kind of this layer that offers the maximum resistance are stacked accordingly so that the tennis racket becomes very strong. In fact, graphite is also used for heat shielding in rockets. You know that space shuttles and all these things, they go beyond the Earth's atmosphere. So on the way up and then on the way down, the rocket suffers a lot of friction with the air molecules. These capsules suffer a lot of friction with the air molecules. So the resistance to the friction is carried out by heat shielding technique. So that heat shielding material is also carbon material, graphite material. So as you can see, graphite can have different properties under different circumstances in different directions. Or you can also think of something like liquid crystal. You'd say, what is this liquid crystal business? Liquid is liquid. Things move freely like in water. And crystal is crystal, very strong, well-defined structure, as in, let us say, ice crystal, right? So ice is solid phase, water is liquid phase. So what is liquid crystal? How can two things have the same property? Well, it can. Along one direction, it can have well-defined crystalline structure, and along another direction, it can have freely moving properties, as in a liquid or as in a fluid. So in such cases, you have different physical properties in different directions. The same principle can apply for electric material also. Incidentally, in this anisotropic behavior, I just gave you simple examples from a mechanical perspective. It can happen in various other cases. Optical anisotropy is also a very useful thing. All your Polaroid technology, polarization, optical polarization, all these things, they use optical anisotropy. A certain material will have a certain kind of, will have transparency in one direction, a different kind of transparency in another direction, one refractive index value in one direction. For instance, in water, water has got the same refractive index in every direction, right? But a material like quartz will have different values of refractive index, different refractive indices in different directions. So that's also optical anisotropy. So here, by the same analogy, we can also have electrical anisotropy, whereby in one direction there could be one kind of polarization depending on the value of chi E in that direction, and in another direction you can have another kind of polarization depending on chi e in that direction. But those are complicated cases. We shall not discuss all that in our course. I just giving you a little flavor of the vastly interesting properties of materials in the world. And these things are intrinsically, these theories or theoretical ideas are intrinsically connected to such things. Whereas, as I said, in anisotropic material, chi e will be in general what is known as a tensor, but you don't have to worry about the tensor business in your course. For our purposes, we shall treat it as a simple scalar. In the tutorial today, we shall take a few problems where we shall work with this formula. Anyway, with this, I finish our discussion on electrostatics. Like I told you earlier, there was a certain skipping of pages. We note that these pages go from this page of polarization notes go from page number 121, whereas we finished our Laplace Poisson kind of discussion at page number 102. So the interim pages were skipped, and also in between I added some additional points on images and dipole moment potential due to a dipole and all that uniqueness theorem in a supplementary sequence of notes going by the tag A1 to A6. So page number 102, just write it. Page number 102, then pages A1 to A6, then pages 121 to 126. That is the sequence we have followed. 126, this is the last page. That is the sequence we have followed. Now, with this, we have finished electrostatics. In case you're wondering why all this confusion and all that, because earlier what we used to do is to first discuss electricity and magnetism in free space and then get into material. But now we have decided that we shall discuss electrostatics both in material as well as in free space first and then get into magnetism. So that is why. I hope you're not going to be too thrown off by that. So we shall now go back to page. We remember I told you we stopped at 102 and made some hop, skip, and jump here and there. Now we shall go back to page 103 and start our discussion of magnetostatics. So formally we have finished electrostatics with today's class. So in about, we have 22 minutes left as per our schedule. So what we shall do now is to take up the initial discussion of magnetostatics. I shall start the presentation. Please bear with me. Can you please confirm that you can see the presentation? Hello?
Yes, sir.
Okay, thank you very much. Please mute your mic, all of you. Right. So here is our first discussion of magnetostatics. This is, if you have had some clear idea of electrostatics, so broadly speaking, our course will have the following chunks or modules, if you like. First, we have finished the mathematical preliminaries, going up to all those divergence curl, etc., Laplacian business. Then the next thing that we have, I mean, vector calculus. First more chunk was vector calculus, mathematical preliminaries. Then we have electricity, electrostatics. Now we are about to begin magnetostatics. Once we have understood electrostatics and magnetostatics, we shall go into electrodynamics involving both electricity and magnetism in very varying time. But for the time being, we confine our attention to magnetostatics. And statics, what does it imply? Statics means that things are unchanging in time. Things are not changing in time. Okay, for instance, electric field not changing in time. Now we are going to talk about magnetic fields that are not changing in time. And how do you get an electric field that are not changing in time? You get an electric field that is not changing in time with the help of charges that are stationary, standing still, stock still. So fixed charges in space give rise to an electric field collectively. Similarly, instead of fixed charges, you do not talk about a fixed current. Current is not fixed. The very word current implies things in motion. You say that the Ganga in the Himalayas has a strong current, meaning the water of the river Ganga in the Himalayas flows very swiftly, strong current. Okay. So you have got a current that is a flow of charges, movement of charges. So how do you bring in the idea of unchanging behavior when unchanging time-dependent behavior when you have something moving? Here's the answer. Here's the discussion. You're talking about steady currents. Steady currents will create unchanging magnetic fields in time. That is the subject of magnetostatics. I'll discuss steady currents in greater detail. First, let us just try to understand this thing. Unchanging electric field, electric, not magnetic. Unchanging electric field in time will be created by fixed charges. Unchanging magnetic fields in time will be created by no longer fixed charges, charges in motion. Unless you have charges in motion, you will not have a current. But what is this current, steady current business all about? Let us now try to see. Suppose you are being made to observe flow of charges in a wire. I mean, you can't really see charges going in a wire. Nature has not given you that kind of an eye. But just imagine this scenario. Flow of, or maybe not even that. Let me just see. You're a traffic police officer. You are observing the traffic flowing past. You have a stopwatch in your hand. What is traffic flow? Movement of vehicles, right? So your boss has instructed you just to monitor the traffic flow at a particular time of the day. So you say that you just make a note of how much traffic is there in the morning, let's say from 9 to 10. What will you do? You have a stopwatch. One way of doing it, you have a stopwatch. You start your stopwatch at, let's say, at 9 o'clock sharply. And you let the stopwatch run for 1 minute. Okay. 1 minute means 60 seconds. And in 60 seconds, sitting at your observation post next on the footpath, you have noticed a certain number of vehicles gone by. Let's say it's very heavy traffic, probably 20 or 30 vehicles would have gone by. Let's say 30 vehicles. 30 vehicles have gone by on a busy road in 60 seconds. So you say that for every 2 seconds as an average, one car or one vehicle has gone past my post. Okay, fine. Then you make your observation, you stop your watch, take a little rest. Again, 5 minutes later, at 9:05, you turn on the stopwatch. So the stopwatch runs for 1 minute, 60 seconds that is. And in these 60 seconds, again, you notice something like 30 vehicles have again gone by. So like that, from 9 to 10, when it is busy hour, you will see that every minute, 30 vehicles are going past. Now, in the morning, you will say that within the rush office hour, there is a steady traffic flow of 30 vehicles per minute. Anytime within that 1 hour, you make an observation, you'll have a steady traffic flow of 30 vehicles per minute. But on the course of the full day, the traffic flow is not going to be as steady as that. Let's say at 4 o'clock in the morning, you're a traffic police officer, you're standing next to the road. Will you see 30 vehicles going past you at 4 o'clock in the morning on a time scale of 1 minute? No, of course not. Probably not even a single vehicle will go past you. Maybe somebody going to the airport to catch an early flight or a train rail station will be traveling, a solitary taxi, one taxi or so, maybe in one full minute. So you see, different times will give you different flow of vehicles per minute. So that is an example of an unsteady traffic flow. But at a particular time of the day, within 1 hour in the morning, rush hour, office hour, you will say that no, at this time the traffic flow will be steady. We have a very busy time. All policemen must be on the alert, police personnel, and do their duty properly. You can have a more relaxed time later in the night or something like that. So that is an example of both a steady flow and an unsteady flow of particles. Why am I saying particles? Imagine the vehicles to be now like particles, charged particles. And you are a scientist making observation, you're no longer a policeman. You're doing the same thing with a wire. Instead of the road, you have a copper wire. Instead of the policeman, there you are in your laboratory. And instead of vehicles traveling down that wire, you have charged particles. So you turn on the stopwatch, you've applied a potential difference across the wire, a battery, you've turned on the stopwatch, charged particles are traveling past you. In 1 minute time, you will say, what is the total number of charged particles that have gone past my post? You'll make a note of that number. Then you rest a little while. After that, again, you start your stopwatch for 1 minute. And in those 60 seconds, which make 1 minute, again, you would have noticed the same number of charged particles going past you. So any time, well, of course, it is much easier for you to control the motion of charged particles to a steady value than for traffic policemen to control the traffic to a steady value. Different times of the day will have this different number of vehicles going past your traffic post in unit time. So that will be an unsteady traffic current, if you like. Unsteady traffic current. But in the laboratory, things are better controlled, so you will have the same potential difference. Of course, your battery will have to be properly charged all the time. So if your battery charge goes down, your battery power goes down, then the current will also become weak. So if you are able to control all those things, what is current? By definition, a current is the number of charges flowing per unit time through a certain point in a conducting material. That certain point is like your observation post. Certain spatial point in a conducting material, that is like your observation post. And so from that observation post, you've noticed 10 charges going past you in 1 second. Anytime you take that observation, you'll see 10 charged particles going past you in 1 second. So you'll say that that is an example of a steady current. The value of the current is not changing from time to time. dq dt, what is current? dq dt. dq dt has got a fixed value. dq, delta q divided by delta t. Delta q is the number of charges going past in a time window of delta t. Delta q by delta t, taking differentials, it becomes dq dt. That value will be a fixed value. So that is an example of a steady current. And if you have a steady current, a steady current will give you an unchanging magnetic field in time. So when I'm talking about statics, we understood things are fixed in statics. But when you're talking about magnetism, you have to have currents. So current is not a fixed business. Current means flow of charges. So what is the fixed thing over here? The fixed thing is the value of the current. The number of charges flowing in unit time has got a fixed value. And as such, it will give you an unchanging magnetic field in time. And that is the subject of magnetostatics. In the early stages of our course, I mentioned to you that disabuse yourself of this idea that there are things like North Poles and South Poles. There is no such thing really as a North Pole or a South Pole in nature. All you have when you're studying electromagnetism, all you have are charges. If the charges are static, fixed in space, you will get electricity. If the charges are moving, then in addition to electricity, which you will always have, you will also have magnetism. So moving source charges will generate a magnetic field. That is what has been written over here. Let us now, like in the case of charges, we have had some observational properties. We had some observations. What are they? That if you have two charges of the same type, they will repel each other. But if you have two charges of the opposite type, they will attract each other. Now we will look at an analogous observation in the case of currents. Suppose you have got two wires. Remember, current, whenever you're talking about current charge, by the way, geometrically also you should be clear about one thing. Whenever you're talking about charges, you can afford to think of a charge as a point-like thing, a dot. But you can't think of such a dot in the case of a current. A current must not be thought in terms of a point. Why not? Because a current requires charges to move. And when they're moving, charges are being displaced. And displacement means an initial point and a destination point. A little bit of length has to be traversed. So current must always be thought of in terms of a line, as in a line element dl, at the very least, but not a point. Charge can be thought of as a point, but a current must be thought of in terms of a small line. It can be a small line, it can be a long line, whatever, but a line. It's a one-dimensional object at the very least. A point charge is a zero-dimensional object, on the other hand. Anyway, so let us make a note of such one observation. I have got two long wires, copper wires, through which, and they are kept adjacent to each other, close to each other. And through these two wires, current is flowing. Both these two wires, there's a flow of current, charge particles. Now, what is the observation that you have? That when these two currents are kept next to one another, if they are going in the same direction, if they're parallel, these two wires will attract each other. But if the currents are two wires, one is, let us say, going from north to south, and the other is going from south to north. If the two currents are going in opposite direction, like let us say two trains going in opposite directions on two close parallel tracks, right? Anti-parallel movement of trains. So if you have that sort of a situation, then these two wires will repel each other. Okay, so that is an observational property. We shall have to explain this observational property in terms of a theory. But before we go to the theory, I will once again stress on this fact that static charges produce an electric field E. Static charges meaning charges that are not moving in space. But if the charges start moving in space, in addition, when I say in addition, meaning that the electric field is still there. In addition to the electric field, the moving charges will generate also a magnetic field. E and B, those are the conventional notations of electricity and magnetism, E and B. Now let us look at one phenomenon which we shall keep referring to, one physical phenomenon observed physically. Remember, we are doing physics once again, and in physics there is no such thing as a mathematical first principle. First principles always come from nature through observations. This is an observational statement. Parallel currents attract and anti-parallel currents repel. Like, let us say, two charges of the same sign repel and two charges of the opposite sign attract each other. This is not a theoretical idea. Nobody has derived this thing theoretically, like Pythagoras had derived his x squared plus y squared is equal to r squared kind of a formula. I mean, base squared plus perpendicular squared is equal to hypotenuse squared. So it's not like that. It's the first fundamental of nature. And here's another fundamental observation about nature. What is it? This straight line that I have drawn with the arrow going upwards is indicating a current I moving from the bottom to the top. The arrow is indicating that direction. Right. The field lines circle around the wire. So when the current is going upwards, charges are in motion, of course. So this moving, set of moving charges, this current, will give rise to a magnetic field. And what is the magnetic field behavior going to be like? Use your right hand. All of you have got a right hand. Look at your right hand. Stick the thumb upwards as we do in a thumbs up gesture, and curl the fingers. So if I is the direction of your thumb and the fingers are curling like this in the anti-clockwise direction, this circular motion, this circle indicates the direction of the magnetic field B. Remember, static charges give rise to an electric field. A current gives rise to a magnetic field. Charges in motion give rise to a magnetic field. What is the nature of electric field due to static charges? You know that already. Take a positive charge, place it at the origin of coordinates, and field lines will come straight out of that positive charge and radiate radially in all directions with no curl at all. Curl will be zero, divergence will be very high. So all the field lines will go out to infinity. Or if you place a negative charge at the origin of coordinates, all the field lines would look like they were coming from infinity and converging at the negative charge at the origin of coordinates. So it will be like straight radiating outwards porcupine quills. But here, when you have a current going upwards, the field lines will not be radiating from this line of current. The field lines will be going round and round in circle along about this or around this wire, around this line of current. So the circular motion, now can you see what is going to be the nature of this field line? We have discussed this thing a lot earlier. This field line has no divergence. Things are not going out. Things are not converging towards the center, but going round and round in circle. So if you have a good geometrical intuition about the behavior of vector fields, then immediately you would be able to sense that this is a zero divergence vector field. But we shall look at it in more mathematical detail later. This is a zero divergence vector field, but it has a lot of curl. Curling motion meaning just going round and round, which is completely opposite of the behavior of the electric field lines coming out of a static charge. They will not curl this way or that. They will just keep moving straight out from the point at the center, and in every direction the electric field lines will go to infinity. A lot of divergence, a very high flux, zero curl. But here, no divergence, zero flux. We have discussed this thing. Divergence is zero. Then by the application of the Gauss divergence theorem, the flux will also be zero, and a lot of curl. Okay, now we shall subject this observation, parallel currents attract and anti-parallel currents repel, to this phenomenon. That if you have a current going up like that, then by the right-hand rule, if the current is aligned with the direction of your thumb sticking upwards towards the ceiling, then your curling fingers will align themselves along the direction of the rotating or the circular magnetic field. Now let us look at this parallel anti-parallel current business. You've got two wires with current going upwards, right? The first wire has given rise to a set of magnetic field. Just like, you know, when you study electrostatics, you have a source charge and a test charge. So let us say that here you have a source current. A source current, what is it the source of? It is the source of magnetic fields, which are going round and round, like that. Okay. Now here's a second current. Call it the test current if you like, and you have placed it in the magnetic field. Now what about this current? What is current made of? Flow of charges. So the charges are flowing upwards in this direction, moving upwards in this direction with a velocity v. And now you follow carefully, this magnetic field line, although it's been drawn on the plane of the paper, is coming out of the plane of the paper and going in at this point. So at this point, the magnetic field line, just give me a minute and I shall finish this discussion. At this point, the magnetic field line is going into the plane of the paper. Whereas at this point, the magnetic field line is coming out of the plane of the paper straight towards your eyes, like that. So it's going round and round in anti-clockwise motion, if you like, if you were to look at it from the top. Okay. So here's the kind of force that a charged particle in the current test wire will feel. Q, if the charged particle has a single charged particle, of course, it's a train of charged particles. If it has got a value Q, the force that it will feel will be V cross B. This force is known as the Lorentz force. This is an experimental law, just like you have Coulomb's law in electrostatics. This is the Lorentz force law in magnetostatics. Anyway, I have run out of time, so I shall stop the discussion over here. In the next class on Friday, we shall take up this discussion in greater detail. We have started discussing magnetostatics. So today we have a tutorial. I'm stopping the sharing. I'm stopping the recording also. Today we have a tutorial at 2 p.m. You'll be given the link.